Welcome to my channel, Linear Algebra. Imagine for a moment you are sitting in front of interviewer and you have been asked why you have used this particular model or algorithm in this particular situation. In other words, the backend process, how this model or algorithm works. To answer such questions, you have to understand the fundamentals. You must know the fundamentals, and that's what we are doing here. Earlier we have seen why we are learning linear algebra, and today we are going to focus on 5 things: vectors, distance of a point from origin, distance between 2 points, row vector and column vector. One of the very basic concepts in linear algebra is a concept of a point or a vector. Let us understand with simple coordinate geometry. Let's assume I have a coordinate system like this. If I have a point here, geometrically this is a two-dimensional surface, and let's assume I have a point P here. This point can be represented with two values. The first value corresponding to how far away is this point. This point is, let's say, 3 units away from origin. Origin basically here is 0, 0. So my point P has two components, x1 coordinate as 3 and x2 coordinate as 1. So this is how I represent a point. We can represent a point basically using a vector. So we can write a vector as P equal to 3, 2, which is two-dimensional vector where 3 is x1 component and 2 is x2 component. Just remember all this terminology I am using. What if I have a point in 3-dimensional space? I have x1, x2 and x3 axes like this, and there is a point here, let's say Q is 1, 3, 5, where 1 is x1 component, 3 is x2 component and 5 is x3 component. That means point Q is 1 unit away from on x1 axis from origin, 3 units away on x2 axis from origin and 5 units away on x3 axis from the origin. This point Q can be represented in vector form as Q equal to 1, 3, 5. This is a dimensional 3-dimensional point, vector of size 3. What about n-dimensional point? Whatever we learn in 2D and 3D in linear algebra, we can use the same understanding for higher dimensional also. We can represent an n-dimensional point in vector form as, let's say, x is equal to 1, 5, 4, 9, 6, 15, etc. Here x has n components. We can't visualize more than 4-dimensional space, but mathematically I can write a point in n-dimensional space by using n components. This is a very simple idea of what a point is. Now let's understand the distance of a point from origin. Let's take 2D example. Suppose I have a point P here with component A and B. That means this length is A and this length is B. This is my origin. This is distance D, which is the distance between origin and point P. We can simply apply Pythagoras theorem to find out D. This length is B, this length is A. D is nothing but square root of A square plus B square. This is in 2D. We can apply the same concept to 3D also. Using the Pythagoras theorem, I can prove that the distance of this point from origin is square root of A square plus B square plus C square. We have seen distance of a point from origin in 2D and 3D. We can apply the same concept to n-dimensional also. For n-dimensional point, let's say P is equal to A1, A2, An. The distance D would be square root of A1 square plus A2 square plus An square. What we have learned in 2D and 3D, we can easily extend it to n-dimensional also. This is the beauty of linear algebra. Now let's understand distance between 2 points. Let's see an example in 2D. Then we can extend this to higher dimensional space. Let's assume I have two axes, x1 and x2, and I have 2 points P and Q. Let's assume P has A1 and A2 and Q has B1 and B2. Now I want to find distance between these 2 points. Using basic coordinate geometry, we can find the distance D, which is nothing but square root of A1 minus B1 square plus A2 minus B2 square. We can find this using Pythagoras theorem. This distance is nothing but B1 minus A1, and this distance is nothing but A2 minus B2. So using Pythagoras theorem, we can find D as square root of A1 minus B1 square plus A2 minus B2 square. Similarly in 3D, if we have 2 points P as A1, A2, A3 and Q as B1, B2, B3, distance between P and Q, if it is D, I can simply write D equal to square root of A1 minus B1 square plus A2 minus B2 square plus A3 minus B3 square. This again we can prove using Pythagoras theorem. Similarly for n-dimensional space, if we have 2 points P as A1, A2, An and Q as B1, B2, Bn, we can write the distance between P and Q as D is equal to square root of A1 minus B1 square plus A2 minus B2 square plus An minus Bn square. Again, the same idea we learned in 2D and 3D, we can extend it to ND. This is the beauty of linear algebra. Let's learn simple terminology and notations here. We have, let's say, vector A as A1, A2, A3, An. Here A has n components, so it has 1 row and n columns. So when we have something like this, we write subscript as 1 cross n. Here 1 represents number of rows and n represents number of columns. We can write A 1 cross n, which means vector A has 1 row and n columns. When a vector has only 1 row, it's called a row vector. Similarly for column vector, if I have a vector B and suppose it has components like this, so here B has n rows and 1 column. It can be denoted by B in the subscript n cross 1, where n represents as number of rows and 1 represents as number of columns. Given a vector or given an array, I can write as a row vector or a column vector. We will see how these are useful. Here I am just explaining notations. Similarly for matrix. Matrix typically represented as A in the subscript m cross n, which means I have a matrix here A which has m rows and n columns. In the next video, we are going to focus on dot product and angle between 2 points, 2 vectors. This is Gunjan Varde signing out until we meet again.